for this one. So when we call stability, we mean a system, a closed loop, any system actually should have outputs. If you have inputs to the system that are limited, the output should be limited. So in a way, bounded inputs should, let's say, produce bounded outputs. This is not very clear. That is, if you have an input that is input to the system is like this, let's say, this is u of t. The output should be also bounded. That is, it should be not going to infinity. Okay. Output. And this is a system like this one again, where there is u is the input, y is the output, and this is the system. Now, for example, a typical classical example of stability is the pendulum. As you know, the pendulum by itself, if you hang it from a wall like this one, this pendulum eventually settles down at this position. So it might oscillate a little bit like this, but eventually it settles down. So this is a stable equilibrium of a pendulum. It is a stable equilibrium point. On the other hand, if you take the same pendulum and put it upwards, like this one, like this, okay? This pendulum at this position is not stable. So this is at an unstable equilibrium here by itself, okay? So it is this kind of, the same system, the same pendulum is stable when it is downwards and it's unstable when it is upwards, for example. This also, for example, if you have let's say, a ball in a potential field like this, this ball, for example, is at a stable...
Can I ask a question?
Yes.
The reason why the inverse pendulum is unstable, we have to move it so that it can stay like that?
No, this is unstable because, well, any small perturbation, if you just touch it a little bit, this will fall down from this equilibrium. Theoretically, if there is no disturbance, this pendulum will stay upwards, you know, without any disturbance at all. But slightest disturbance will make this thing go down. So the equilibrium position can be disturbed. Whereas if you disturb the equilibrium position of the downward pendulum, it will eventually come back to the same equilibrium. Do you understand? The same thing, for example, for a potential field with a ball like this, or another field like this one. A ball at the top of the hill, like this one, is unstable, for example. If you push it a little bit, it will go down. Whereas here, if you push it, it will eventually come here and stay here. That's one definition. That's another way of looking the stability of systems. Certain systems, you know, keep their orientation. Certain systems do not keep their orientation, okay? Well, the physical systems we are dealing with, for example, the mechanical systems, like a mass spring damper system, let's say, like this one. Okay. Let's say E. This system has an equation of mx double dot plus bx dot plus kx equals, let's say, 0. Let's say we are looking at initial conditions only. Okay. Now this system, the mass obviously has to be greater than 0. But in order to have a stable system, you should have B and K must be 0. This means positive damping, which dissipates energy. And this means K greater 0 means positive spring or positive pullback effect. Let's say positive, let's say pull back. What if the damping is not 0 or it is negative, let's say? If B term is negative, then the damping adds energy. Instead of removing energy to the system, it adds energy to the system. But how can this be? It is possible. There might be certain, devices which add energy to the system. So it is possible to have a term that is a negative. If B term is negative, you will have negative damping. So it will be unstable. So B less than 0 or K less than 0 means unstable system. Okay. That is, the oscillations of this system is going to grow up eventually over the time.
Hojam, I just had a question.
Yes.
So far, we've only been dealing with positive damping and pullback, right?
Yes.
We haven't had the negative
Yes,
case.
yes. Well, normal physical systems have, B and K terms are always positive. Actually, I told you before that in your equations, if there is something, if you get a negative term there with a physical system, you'll probably have made an error, because you shouldn't be getting that, because these systems are passive. Systems are like these are passive systems, so they shouldn't be negative. So if you, in your derivations, if you get a negative term, it means that you are probably making an error. Okay. So if, for example, if B is less than 0, for example, the response of your system will look like this. Time response, let's say x of t. It will start from here, but the oscillations are going to, I cannot draw it very well, but you can understand. Something like this, okay? It just becomes bigger and bigger. Amplitude becomes larger and larger until the system breaks down, obviously. Eventually, such systems break down, reach their limits, or, materials fail, or something like this. So, unstable systems are not desired. We try to avoid them. And in control systems, we try to keep the systems in the range of stability. If you have a linear system, for example, you have the transfer function of your system will be the numerator over the denominator. And we have shown that before. I have shown you that stability is determined by d of s must have roots, let's say, with negative real parts. This is the condition for stability, okay? That is the poles of G of S. We talked about the poles of G of S. Poles of G of S are, as you know, are the roots of D of S. Let's call them Pi, okay? Then the real parts of Pi must be less than 0 for all I values. Okay, this is an I. So the poles of the system must be negative. If one of them is positive, unfortunately your system is going to be unstable. So if you look at the complex plane, for example, if you plot the poles, this is the limit for stability, the imaginary axis. This is the real. If the poles are here, these poles are all stable. But if there are one single pole here or here, these poles will be unstable. Because the oscillations caused by these poles are going to grow up over the time. For example, if you have a system, let's say, one pole of your system is, let's say -3, 2, 3 is minus, let's say, 0.5 plus minus 1J. Okay. For example, this system with 3 poles is stable because all the poles have negative real parts, as you see. This is negative, so it's okay. But on the other hand, if you have another system, P1 is, let's say, positive 0.1, P2, 3 is -5 plus -10J, let's say. Unfortunately, this one is, as you see, is positive, so this is unstable. We can show this actually. Go to MATLAB and try it, for example, MATLAB or Octave or whatever, and show that the response of such a system is actually unstable, okay? It will eventually grow up. Actually, it's not too hard to...
Hojam, I have a question.
Yes.
So, Hojam, if just one pole is positive, it will affect the whole system?
Yes, even a single positive pole makes the whole system unstable.
Okay, thank you.
Let me actually illustrate this using okay, you can see it, right? The octave. I hope. So, for example, let's say that the denominator is 1. Numerator is 1. Denominator is, let's say, 1, 3, 5, 2, let's say. G is the transfer function of N and D. I think we need to write the load, this package load control. Okay. Okay. So pole of G. Okay. Now we see that the poles of this system is, or they are all negative. So let's look at the step response of this system. It takes some time. This is stable, as you know. We can change this a little bit. Let's say 1, 3, 5. Let's make it 7 or something like this. Sorry. This is still stable.
Hocam, don't we need to change the signs like -5s or?
I know. This is
Oh,
still
sorry.
stable. Now, this is still a stable system, as you see. You see the step response. But eventually, if, for example, I will change the D term, let's make it 20 or something, the last term. I'm just making this up, actually. So our system is this one now. Let's look at this poles. You see, now 2 poles have become positive. Now let's look at the step response. This one will be unstable, as you see. As you can see, it will start from a very low value, but eventually the response is going to grow up. This response is unstable, as you can see. Okay? So systems gets unstable when their poles have positive real parts. So let's close this one. Let's stop this and let's share just the whiteboard. Okay. Now the problem is this. You have a large system, let's say. Let's say the denominator of your system is s to the 4 plus 3s cubed plus, I'm just making this up, 5s squared plus 6s plus 10.
Hocam, in the example for the unstable part, why is the -5 plus minus 10j in the unstable part? Isn't the real part negative over there? For P23.
I didn't get the question, I'm sorry.
Hocam, in the example that you just wrote this for P1 and P23, the stable and the unstable part. In the unstable part, why is P23 equals -5 unstable?
I just made them up. There is no reason.
No, but Hocam, if it's negative, shouldn't...
As long as it's negative, it's okay. This is okay.
But it's negative here. No, but isn't negative for stable?
Negative is for stable, yes. This is the problem one.
Oh, okay. Thank you, John.
The poles should not have positive real parts. They should have all negative real parts, okay?
Thank you, John.
Okay. Now, how do we know? Just by looking at this, can we find whether this is stable? This is a stable system or not? Well, it's not very easy. You know, just by looking at it, we cannot have an idea. Well, there is a way. You can just, you know, enter them to MATLAB or something and find the roots. If you find the roots, and if all the roots have negative real parts, then you can say that this system containing this denominator will be stable. But we want something more than this. We want to find out a method to analyze stability without, finding the roots of this system, because this can be a tool for the design as well. So we want to find out, let's say, stability without solving for the roots of B of S. Well, fortunately, there was a method that was developed in the 19th century. That was the root criterion for stability. Well, it was exactly that. First of all, there is one thing. Let me just write this down, the root criterion. Just by analyzing the coefficients of D of S, you can find the stability of a system. So if you have a D of S, let's say, this happens all the time, I have no idea. So I have included a coefficient for A, and usually we take it to be 0. So this is D of S. We have the coefficients. We want to find out whether such a polynomial has poles with negative real parts. So the question is, does D of S with negative real parts? Okay. We want to find this out. This is trivial for simple systems, but for large systems, this might be a problem, and we can use this as a tool for design and analysis. Now, there is a necessary condition only. Necessary condition, which is called the Hurwitz test, by the way, is that all coefficients AI, okay, must exist in the first place. That is, they must be non-zero, and this is only more important, they must all have the same sign. Well, this basically means that they should all be positive, okay? They can also all be negative, but if not, this means that your system is unstable. But if this is satisfied, it doesn't mean that your system is stable. So it is a necessary condition, but not a sufficient condition, okay? If this is satisfied, this still does not guarantee stability, but non-existence of this guarantees instability, okay? This is not enough. This is not a exact condition. But this test this test must be passed for the system to be stable. So this, let's say, condition is not sufficient or enough. Let me give you an example. For example, if d of s is, let's say, 3s to the 4 plus s cubed plus 4s squared plus 5. There is no s term here, 0 times s, okay? It is obvious that this will be unstable. This thing will have poles with negative real parts. Okay? If d of s has, again, s to the 5, let's say, another one, 4s cubed minus 6s squared. I'm just making this up, 8s plus 14, okay? Because of this negative term, and also that the fact that, well, s to the 4 term is missing, this is unstable also, because of here and because of here, this is unstable. But this one, for example, 3s to the 4 plus 4, let's say, s cubed plus 5s squared plus 8s plus 5. Is this stable or not? We have satisfied all the we have all these terms are positive, but we cannot say that this system containing such a denominator would be stable. We cannot conclude, we can't say if this system is stable. Except for first and second order systems, in which this is sufficient condition. For, let's say, first and second order systems, this is enough. That is Hurwitz's test, let's say, is also sufficient, which means that the system, first and second order systems, are stable if all the coefficients are positive. You can immediately say that. The real condition for stability of a system, necessary and sufficient condition, is determined from the root test, as we have said. We have to, generate an array from our system. Let me see. Let's say that again, d of s, the denominator of our system is a n s to the n plus a n minus 1 s plus a1s plus a0. Okay, this is our polynomial. We have all the coefficients, and now we will generate a array out of this, and we will do it this way. The first two rows we will write, let's call it s to the n here, s to the n minus 1. The first two rows are, you start with an, then you skip the 1 and go to an minus 1, okay, sorry, an minus 2, that is, you skip 1, then you go to an minus 4, etc., and go on, form the first array, the first row. Then in the second row, you put an minus 1, an minus 3, an minus 5, etc. You go on like this. Now, the rest of the rows you generate from these rows. Let's say s to the n minus 2, s to the n minus 3, and you go on like this. S, let's say, squared, s to the 1, s to the 0, like this. Now, let's call this row B1, B2, B3, etc. And you have C1, C2, C3, etc. You know, it won't be this big usually, but, and this will go on like this. Let's call this E1, let's call this F1, let's call this one G1. Now, the important thing is the first row, sorry, first column. Obviously, I have to define this B1, C1, etc. things, but let me just put this in a bracket like this one, okay? Now, how do we determine this B1, B2, B3, etc.? There's a kind of a formula. It's not very difficult. B1, for example, is the negative determinant of this array, an minus 2, an minus 1, an minus 3, divided by a1. This is b1, okay? This b1 is determined from the determinant of these things above. b2 is determined, again, in a similar fashion. Again, the negative determinant of, again, an minus 1. But here you have an minus 4 and an minus 5. Okay? And so on. For example, B3 would be, again, negative determinant of an minus 1, an minus 6, and an minus 7, for example. And, for example, C1 would be determined from B1 and the two things above, which will be the following: minus negative determinant of, this is kind of an minus 1 B1, an minus 3 B2, divided by B1. And similarly, lastly, C2 would be, again, you divide by B1, the negative determinant of this 2 by 2 thing, an minus 1 b1, an minus 5 b3, and so on. Okay, you get the logic here. Now, I hope you get the logic. The important thing is here is that for stability, the sufficient condition, necessary and sufficient condition for stability, all terms must be positive. Okay, all terms in the root array, the first column of the root array, all of the terms in the, let's say, first column of the for all the roots to have negative real parts, all the terms in the first column of the root array must be positive. Okay. Okay, I'll give you examples, but let's take a break at this point.
Hujam, is
Yes.
it possible if you could scroll up, because I think I missed something.
Okay, sure.
Up. No, could you go more up, because it was like the graph part.
Graph.
Well,
we are.
Yes, yes.
I'm recording this, so you can just check the recording later.
All right.
Hocam, may
Yes.
you explain again? I think I missed the part. What is the logic behind that we are taking the determinant of those terms?
Well, there is
It
the
gives
logic
the
is it is a mathematical procedure. The proof is a difficult one. I cannot give it to you at this point. I just ask you to accept it. You know, it's a mathematical proof. It just shows that if this is true, and if the determinants are computed this way, eventually the array that is determined by this procedure is going to give a first column like this one, and the elements are going to be if all the elements in the first column are positive, then the D of S are going to have roots with negative real parts. Okay, that's a mathematical proof, but I think it will be, you know, too much to give the proof, and that's not our aim to, you know, to prove this mathematically. We will just use this result. Okay?
Okay, hocam. Thank you so much.
Okay, I'll stop the recording.